Dear students, welcome back to another lecture on structural analysis. So in this lecture, we will be dealing with module 5. We'll be dealing with module 6, which is related with plastic analysis. We will be having a few lectures related to this. Let us start with the basics of plastic analysis. The conventional analysis that we have learned till now, we call it as the elastic analysis or the working stress method. Okay, what we have learned till now is the working stress method. So what is the basis of the elastic analysis or the working stress method? So in this working stress method, imagine let us have a simply supported beam and let W be the load that is acting on the simply supported beam. So in the working condition, or let us say in the service condition, so in the working condition or in the service condition, the stress at any point in this particular beam is not allowed to exceed what is known as the allowable stress. So at no point the stress should be greater than the allowable stress. That is the idea of working stress method. And the failure load, we are assuming that the failure load is reached when the stress at any point reaches the yield stress. Okay, so the failure load, we are assuming that the structure will fail if the stress at any point reaches the yield stress. Okay, so this is the idea of the working stress method. And how do we calculate this working stress as well as the failure stress? The allowable stress or the working stress is assumed as the yield stress divided by a factor of safety. So this is how we calculate, and as you know, if the cross-sectional area is A, you can calculate the working load as the allowable load multiplied by the cross-sectional area, and you can calculate the failure load or the ultimate load as the sigma y multiplied by A. So this is how you calculate um, the working stress method. Now what is happening in this working stress method is that we are only considering the uh, linear portion of the stress strain curve. That is, if we consider the stress strain curve of mild steel, the stress strain curve of mild steel is like this. You will have a linear portion and then there is an upper yield limit, lower yield limit. Then you will have a yield plateau. Then there will be a strain hardening region. Then the material reaches its ultimate stress and then there will be necking and finally there will be a breaking point. So what you can see is that the even after the material reaches the ultimate the yield stress, this will be the yield stress. This is the yield stress. So the material reaching the yield stress doesn't mean that the material is failing. It is still capable of taking load up to the ultimate stress. So that is one factor. Another factor is that steel as a material is capable of undergoing taking larger strains. So for example, the strain at which the yield is reached is this value, whereas at failure the strain is much more, or even this strain at the ultimate stress is much more as compared to the strain at the yield stress. That means it is capable of undertaking larger deformations. Also another factor we have to consider is that for example, if you are having a simply supported beam and when we are loading it, the maximum stress will be occurring at the, imagine we are considering a rectangular cross section. We have learned the bending theory. The maximum stress will be occurring at the extreme fibers. Okay, so when we say the failure criterion in elastic analysis, the failure criterion is that a failure occurs when stress at any point, okay, stress at any point is equal to sigma y. This is when failure occurs. For example, if you are having a rectangular beam simply supported subjected to central concentrated loading, the maximum bending moment section is going to be nothing but the central cross section. This central cross section will be the maximum bending moment section. If we try to draw the cross section, it will be a rectangle, and as we know, only the extreme points will be having maximum stress. The interior portions will be having a stress that will be much lower than the this yield stress. That is, only the extreme fibers of any particular cross section are stressed to failure, whereas the interior points of the cross section are still under stressed. They are still under stress. That means those portions are still capable of carrying more load. So the elastic analysis basically underestimates the ultimate load carrying capacity of the cross section for several reasons. One reason is that we are only considering the linear elastic portion, and the stress that it can take is higher than that. That is the ultimate stress. And also another thing is the strain that is it is capable of taking is much larger. So there are two reasons. One is the stress it is capable of taking is much higher than the yield stress. Second is the strain a material is capable of taking is much larger than the yield strain. And the third reason is the cross section. We are assuming that failure occurs when any one point in the cross section reaches, that is the extreme fiber reaches the yield stress. However, all other internal fibers in the cross section remain under stressed. Okay, and they are still capable of carrying more load. So to counter all these limitations of the elastic theory, we have what is known as the plastic theory. So let us try to see what advancements the plastic theory is making. So there are certain assumptions that we have to do in the plastic theory. Assumptions in plastic theory. So assumption number one is that as we told, though we have a real stress strain curve like which is having strain hardening everything, in the plastic analysis we are only going to consider an idealized stress strain curve. Okay, so in plastic analysis we will only be considering an idealized stress strain curve which is elastoplastic. Okay, so we will only be considering an elastoplastic, perfectly elastoplastic stress strain curve. Okay, so perfectly elastoplastic stress strain curve is considered in the analysis. So that is one assumption. Second assumption is we are assuming that the modulus of elasticity in compression and the modulus of elasticity in tension remains the same. That is, the material is having the same properties in tension as well as in compression. So modulus of elasticity in tension is same as modulus of elasticity in compression. That is, material is having same behavior in tension as well as compression. The third assumption that we are assuming is the same assumption as that we have learned in our elastic analysis or the theory of pure bending. That is, plane sections remain plane even after bending. So plane sections remain plane before and after bending. So this is another assumption that we have. Plane sections remain plane before and after bending. This is the next assumption that we have. So what this means is we are neglecting shear deformation. Okay, shear deformation is neglected. So these are some of the assumptions that we have with regard to plastic analysis. Now let us try to see what exactly is happening in plastic analysis. So again, let us go to a simply supported beam which is made of rectangular cross section. Okay, simply supported beam made of rectangular cross section given by a load W. And the most critically stressed section is, of course, when it is central concentrated, the most critically stressed section is the central cross section. And let us consider the central cross section and the stress distribution in the central cross section, the most critical section. So what we are going to consider is stress distribution in the critically section. So critical section when central concentrated load will be nothing but the mid section where the bending moment is maximum. So first case is, case number 1 is when the load that we have applied is less than the working load. When the load applied is less than the working load. So the stress distribution in the cross section will be like this. And what will be the stresses at the extreme fibers? The stresses at the extreme fibers will be less than the allowable stress. The second case is when the load applied is equal to the working load. In this case, the stress distribution would again be like this. However, here the stress at the extreme fibers will be same as the allowable stress. The third case is we have put the load equal to the ultimate load. Okay, so when the load is equal to the ultimate load, what happens is the stress in the extreme fibers reaches the ultimate stress. So in elastic analysis, what we are going to do is we assume that the structure fails when this situation has been reached in elastic analysis. That is, any point in the critical section reaches a stress equal to sigma y, then we say that the structure has failed. That is the idea in elastic analysis. However, in reality, all the fibers that are on the interior portions, these fibers are having a stress much less than the yield stress. They are under stressed and therefore they are capable of taking much more stress and more load. So we are going to make use of that. So what do? We try to increase the loading. So when we try to increase the loading, that is when a load is applied and this load is greater than the ultimate load, what is going to happen is the interior fibers also start reaching the yield stress. So here if you see, some of the interior fibers have also reached a stress equal to the yield stress. Not only the extreme compression fiber, but some of the interior fibers have also reached the yield stress. So this kind of a situation we call it as partially plastic section. Okay, so this is known as partially plastic cross section. This is partially plastic section. Now if we continue increasing the load and let us say the load reaches a value W equal to WP, which is known as the plastic load. So in this situation what happens is the entire cross section becomes plasticized. The entire cross section has become plasticized. That means every single fiber in the cross section has reached a stress equal to the yield stress. So this kind of a section we call it as the fully plastic section. So this is fully plastic section. And when a section is fully plastic, we say that it has formed what is known as a plastic hinge. Okay, when a section is fully plasticized, we call it as it has formed a plastic hinge, and this plastic hinge has large rotational capacity. At the same time, it has a load carrying capacity equal to the plastic moment capacity. Okay, it has a load carrying capacity equal to the plastic moment capacity. So this kind of a situation is known as a plastic hinge. Once again, let us try to see the difference between the internal hinges that we have learned. For example, we have learned what is known as an internal hinge. So if you are considering an internal hinge like this, what this means is this internal hinge is not at all capable of carrying any moment. So what happens is, when we have an internal hinge like this in a simply supported beam, it is not at all capable of resisting moment, and it instantly deforms like this. This is what is going to happen in case of an internal hinge. Whereas in case of a plastic hinge, what happens is, this plastic hinge is capable of carrying a moment. Here it cannot carry moment. Whereas in case of a plastic hinge, what happens is, it is capable of rotating just like that of an internal hinge. It is capable of rotating. However, at the same time, it is also capable of carrying moment that is equal to the plastic moment. Okay, so this can carry moment which is known as the plastic moment. So both can rotate at very large magnitudes. However, the internal hinges, they are not capable of carrying moments, whereas in case of plastic hinges, they are capable of transferring moment. That is the difference between an internal hinge as well as a plastic hinge. Now what we have to do is, we have to develop certain relations regarding this. So let us try to see further. So let me take a rectangular cross section. So if we consider a rectangular cross section, and if we assume that the cross section is fully plasticized, this is a fully plasticized section, and even in a fully plasticized section, the equilibrium has to be satisfied. So for example, the force in compression should be equal to the force in tension. For equilibrium, force in compression should be equal to the force in tension. That is, the force equilibrium has to be satisfied for the cross section. So if we try to do that, we will see that sigma y into area in compression is equal to sigma y into area in tension. So since sigma y is the same, we can see that the area in compression has to be equal to the area in tension. So what that means is, this line is known as the plastic neutral axis. Okay, this plastic neutral axis divides the cross section into two areas of equal proportion. Okay, or the plastic neutral axis is also known as the equal area axis. That is, the plastic neutral axis divides the entire cross section into two halves of equal areas. So here the area will be a by 2, and below the plastic neutral axis also the area will be a by 2. So that is the first relation. That relation we have derived from the force equilibrium of the cross section. Now let us consider the moment equilibrium of the cross section. So if we consider the moment equilibrium of the cross section, let us say this is y1, and this centroidal distance of this force from the plastic neutral axis is y2. So if we try to do that, if we take moment about the neutral axis, we will see that the plastic moment capacity is nothing but moment of the forces about the plastic neutral axis. That is nothing but the plastic moment capacity. So that will be Fc into A1. This will be the Fc into Fc is the force multiplied by y1 plus Ft is another force multiplied by y2. So Fc is nothing but sigma y into Ac into y1 plus sigma y into At into y2. So we can take sigma y outside. So this AC into y1 and a1 into at into y2, if we write it as a common term, we can write it as a1 into y1 plus a2 into y2. So instead of AC and I'm replacing it by a1, and instead of at I'm replacing it by a2. So as a general format, what we can do is we can write this equation as sigma y into sigma ai yi. Okay, in this format we can write the equation for MP. So if we try to write a general equation for MP, we know that in elastic analysis we have found out M is equal to F into Z. Okay, so the elastic moment capacity, or what we can call it as the yield capacity or the yield moment capacity, My, can be written as sigma y multiplied by Z, where Z is the elastic section modulus. So we can write an equation like this. Now the equation for plastic moment capacity we have derived earlier is nothing but sigma y multiplied by sigma of ai yi. Now this term ai yi, we can replace it as mb is equal to sigma y multiplied by zp. Okay, mb is equal to sigma by multiplied by zp. So if you look into this, these two formula are now analogous. Okay, these two formula are now analogous, and we can call, if Ze is the elastic section modulus, Zp we can call it as the plastic section modulus. Okay, so this is the formula for the plastic moment capacity, and plastic moment capacity is nothing but sigma y into Zp, where Zp is the plastic section modulus. Okay, so once again, the elastic section modulus, we know it is I divided by y max. Now the plastic section modulus Zp is sigma into ai yi. And what is this sigma ai yi? Let us try to see what is sigma ai yi. Imagine we are having a cross section like this. Okay, imagine we have a cross section like this, and let us imagine that the plastic neutral axis is somewhere here. Okay, imagine that the plastic neutral axis is somewhere here. This is the plastic neutral axis. So if you try to draw the section force, this will be the stress distribution. Now if you try to see, we have different segments of area available on either side of the neutral axis. The total area above the plastic neutral axis will be a by 2. The total area below the plastic neutral axis will also be a by 2. However, they are of different shapes. So in that case, what we do is we will divide this area into different segments. For example, this will be a1 and this will be a2. This area would be a3, and this area would be a4, and this area would be a5. And what are these? So ai means a1, a2, a3, a4 and a5. And what are these yi is nothing but the centroid of each of those areas from the plastic neutral axis. For example, the centroid of this area from the plastic neutral axis will be y1. The centroid of this area from the plastic neutral axis will be y2. The centroid of this small area from the plastic neutral axis will be y3. The centroid of A4 from the plastic neutral axis will be y4 and the centroid of a5 from the plastic neutral axis will be y5. So this entire would give you summation of this product is going to give you, that is ZP in this case would be ZP is equal to a1y1 plus a2y2 plus a3y3 plus a4y4 plus a5y5. So this is how we calculate the plastic neutral axis, and of course the unit is mm cube. Okay, so this is how we calculate the plastic section modulus. Now let us also try to see how another term which is known as the shape factor. Shape factor is considered as the ratio of the plastic moment capacity to the yield moment capacity. Plastic moment capacity to the yield moment capacity. So plastic moment capacity is nothing but sigma y into ZP divided by yield moment capacity is sigma y into ZE, and sigma yn cancels, so we can write this as ZP divided by ZE. So if you want to calculate the section modulus, the shape factor, all you have to do is either take the ratio of the plastic moment capacity and the yield moment capacity, or what we can do is we can take the ratio of the plastic section modulus and the elastic section modulus. And obviously we know that the shape factor will always be greater than 1, as the plastic moment capacity will always be greater than the yield moment capacity. Okay, so